Hello to everyone. Welcome to the course on numerical linear algebra and application. Now we are going to learn 47th lecture and 10th module of this course. Before going to the contents of this lecture, let us quickly recall what we have done in the previous lecture. In the previous lecture, we spoke about convergence of the iterative schemes. We also used a specialized criteria called conjugate gradient method. Now today we are going to do some examples related to conjugate gradient iterative procedure and some other topics. As a matter of simplicity, let us consider a 4 by 4 matrix of this form, and X is a column vector -1 0 1 -1. Let us take X of 0 is 0 0 0 0 transpose. Then R0 is Ax of 0 minus B, that will be equivalent to minus B 1 0 minus 1 1 transpose. R of 0 is equal to Ax 0 minus B, that is minus B will be equivalent to 1 0 minus 1 1 transpose. And D of 0 is equivalent to minus R of 0 minus 1 0 1 minus 1 transpose. We have three preliminary calculations to make before determining the step size lambda. Delta 0 is equal to R0 transpose, and R0 transpose is 3, and U is equal to AD0, that is 5 by 4 comma 1 over 2 comma 3 by 2, which will be minus 5 by 4 transpose, and D of 0 transpose of U will be equivalent to 4. Therefore, lambda naught will be equivalent to delta 0 upon D0 transpose of U, that is 3 by 4, and X of 1 is equivalent to X0 plus lambda naught times of D of 0, that will be equivalent to minus 3 by 4 0 3 by 4 minus 3 by 4 transpose. The residual associated with this new approximate solution is given by R of 1 will be equivalent to R of 0 plus lambda naught times of U, which will be equivalent to, this is R of 0 and this is lambda naught and this is the vector U. So when you multiply the matrix and add up to this R naught, you would end up with a matrix of this size, that is 1 over 16, 3 over 8, 1 over 8, 1 over 16. And the delta of 1 is equal to R of 1, and R of 1 is equal to 21 upon 1 to 8. Then alpha naught is equal to delta of 1, delta of 0, which is 7 over 128. And D of 1 is equal to minus of R of 1 plus alpha naught times of D of 0. So that will be equivalent to minus 1 over 16 minus 3 by 8 minus 1 over 8 minus 1 over 16 plus 7 upon 128 times of minus 1 0 1 minus 1, which is equal to minus 15 by 128 minus 3 by 8 minus 9 by 128 minus 15 upon 128. This completes the first iteration. To start the second iteration, only two preliminary calculations are needed to determine the step size lambda 1. So I will write it as u is equal to a times of d of 1, that will be equal to minus 3 upon 512 minus 81 upon 256 minus 3 upon 256 minus 3 upon 512 transpose, and d of 1 of transpose of u is equal to 495 upon 4096. Recall that the value delta of 1 is nothing but R1 of transpose, which will be equivalent to 21 upon 128 from the iteration. So therefore essentially you do get lambda 1 is 24 upon 165. And x of 2 is equal to R of 1 plus lambda 1 times of u, that is 3 by 55 minus 3 by 55, 6 by 55, 3 by 55 transpose. To complete the second iteration, we compute delta 2 is equal to R2 transpose R2, which is equal to 63 upon 3025. And alpha 1 is equal to 384 upon 3025. And d of 2 is equal to minus r of 2 plus alpha 1 times of d of 1, which will be equivalent to minus of 42 upon 605, 21 upon 3025 minus 357 upon 3025 minus 42 upon 605 transpose. For third iteration, we make the following calculations. That is, u is equal to AD2, so minus 126 upon 3025, 126 upon 3025, minus 252 upon 3025, minus 126 upon 3025 transpose. And d2 of transpose of u is equal to 2646 upon 166375, and lambda 2 is equal to 55 upon 42, and that is for the second iteration. If you look at the third iteration, x3, x2 plus lambda 2 of d of 1, so which is nothing but this value, and similarly R3 is nothing but R2 plus lambda 2 times of u, this 0 value. Thus three iterations of the conjugate gradient method have produced the exact solution, as we could see from this note. Let us look at into Krylov subspace methods for linear systems. How actually the Krylov subspaces, they play a vital role in trying to find out the solutions to the engineering systems. One is the Langkos-Arnold method, second one is the generalized, the residual method, and the conjugate gradient method, which we have seen, and QMR method. So given n by n matrix A and n vectors x, the sequence you write it as x, ax, a square x, like that I will have an minus 1 x1. This is what we call Krylov sequence, and the matrix x, ax, a square x, an minus 1 x is called the Krylov matrix. So which we also denoted by Krylov matrix of order n, a and x. The subspace KMAX, that is span of x, xax, am power m minus 1 x, is what we call Krylov subspace of dimension m, assuming that the vectors are independent. Two basic Krylov subspace methods are the Langkos method and Arnold method. Historically, Langkos method developed by C. Langkos with the first of its type, when the matrix A is symmetric matrix. Both methods have become identical if the starting vectors appears to be the same, but this is not always practically possible. The Arnold and Langkos methods are used as projection methods in numerical linear algebra to solve large scale matrix computations problems which are typical in nature. A Krylov subspace method for large systems is typically projected into a Krylov subspace of a dimension m. So, since we are handling the rectangular matrices m is less than n, then the projected problem is to solve by using a standard technique, and finally an approximate solution of the original problem is retrieved from the solution of the smaller projected problems. We will describe the basic Arnold's and Cankos method first and then discuss some of the well-known applications of linear systems and eigenvalue problems. As all of you knowing very well, Arnold faced full orthogonalization and Gram-Schmidt orthogonalization process for non-symmetric linear systems. They do also possess the similar properties. Non-symmetric Lankos-based biconjugate gradient method and QMR method for nonlinear systems. So, symmetric Lankos-based conjugate gradient method and preconditioned conjugate gradient methods for symmetric positive definite matrices. That's one of the example which you can draw from the project. The Lankos method for the symmetric eigenvalue problems. So, an explicit restarted Arnoldi algorithm for the non-symmetric eigenvalue problems. The implicit Arnoldi method for the non-symmetric eigenvalue problems. So, there are some drawbacks to these methods. Both the Arnoldi's and the Lankos methods might encounter breakdowns or near breakdowns during the process of orthogonalization. In case of the Arnoldi's and symmetric Lankos methods, such as breakdown is considered to be a happy breakdown for the eigenvalue problem, because in such a case one obtains an exact value with the non-symmetric Lankos method. However, this is not always positive or not always true. So, what is the basic Arnoldi method is, given a matrix A belongs to R of n over n, a non-zero vector V such that is m is less than or equal to n, the idea is to create the set of m plus 1 orthogonal vectors x1, x2, xn and an m plus 1 vector Heisenberg matrix H such that V is equal to V1, V2, Vm, and Vm plus 1 is V1, V2, that is Vm plus 1. So, you can write in the matrix form A of V1, V2, V3, Vm is nothing but V1, V2, V3, Vm plus 1 multiplied with this matrix H. From the above, it follows that if you set V1 is equal to, that is V1 upon norm of V2, then we can compute at step k the vectors Vk plus 1 and the kth column of Hk, kth column of Hm tilde bar by comparing the entries of the kth column of the both sides as shown below. So, if you look at in step 1, compute V2 and the entries of the first column of H. By comparing the entries of the first column of the both sides of the above equation, so we do arrive a matrix of this form. AV1 is equal to H1 V1 plus H2 V2 multiplying by V1 transpose on both sides. So, that is nothing but that V1 transpose AV is equal to H1 V1 H1 AV1. Since V1 transpose V1 is equal to 0 and V transpose V1 times of V2 is equal to 0. So, we can write very closely these relations. Next, we will consider V bar is equal to V1 minus H1 V1 and take H2 is equal to V2 tilde. Then we can write this V2 is equal to V bar H22, that is equal to V bar of norm of V2. The other steps are as follows. Step 1 is at static step, the component of the kth component of the matrix Hm with k plus 1 can be generated from the k plus 1 term recursive relations. So, AV of is equal to H1 V1 plus H2 V2 etc. linear combination, and then also it becomes the basis. Algorithmically, Hk will not be computed from the relation, that is Hk is equal to V transpose AVk. Thus, the above process is simply the modified Gram-Schmidt orthonormalization process. We will now rewrite the process algorithmically in the following. There exists a household proportion of the matrix, we will write it as, that is the Arnold method for this modified is, you are given n by n matrix, square matrix, and n vectors, and a positive integer less than or equal to n. Output is, let set am plus n orthogonal vectors and v1, v2, v3, vm, v transpose, and step m plus 1 is m Heisenberg matrices A is equal to av1. Normalize the vector to obtain v1, where v1 is equal to vector by its magnitude. So we like this code will do the job which we are supposed to do it. Now v is equal to v1 bar minus v2. So this also can be used in the some of the popular roads. And end product is nothing but, so e1 v1. So they were bought from this code. So it is a little bit developed by the group of researchers, and it serves as a basic literature for the future work. So I gave today very small introduction to conjugate gradient method and its applications. I am sure all of you might have learned it, and tomorrow we will solve the Krylov space and Arnold method, and we will go ahead up. Thank you very much for listening to my lecture. Thank you.